Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 15, 2025, about 3 days ago. This paper introduces Iceberg, a task-centric benchmark that shows how sky-high synthetic recall can still fail downstream, like cases where recall at 100 hits about 99.9%, while label recall at 100 stalls near 71%. The paper is titled, Reveal Hidden Pitfalls and Navigate Next Generation of Vector Similarity Search from Task-Centric Views. Alright, the diagnostic idea called the information loss funnel ends up being the key to why those rankings flip in practice. Also, the authors shared an Iceberg GitHub repo that serves as the benchmark suite behind the paper. You will find C++ and Python code to run end-to-end vector similarity search evaluations, configs for datasets and algorithms, baseline implementations, a Docker setup, and scripts like run.py and evaluator.py to build, search, and score across multiple real-world datasets. Figure 1 makes the core point concrete. A great recall score can still mean poor task usefulness. Synthetic recall measures distance-based nearest neighbors, while label recall checks whether retrieved items share the right identity or class, so it reflects real task success. On the left, label recall flattens, even as synthetic recall keeps rising with more query time. On the right, inner product distance reaches high synthetic recall, but label recall stays near zero. Figure 2 explains how Iceberg turns that synthetic versus task mismatch into a practical selection workflow. The left panel lays out 3 layers: application, embedding, and method, so the benchmark connects real tasks like ImageNet and Glink 360K to specific embedding models and index families. The right panel presents a decision tree that uses quick meta features, meaning simple geometry checks of the vector space, to pick a similarity metric and then shortlist leading methods. Table 1 clarifies why Iceberg is meant to change how people compare vector similarity search systems, because it claims to measure real task impact and not just distance-based accuracy. This table lays out the full comparison grid across benchmarks. The left column lists popular suites like AND benchmark, big AND benchmarks, big vector bench, and MTEB. The rightmost columns highlight that only Iceberg reports downstream utility and provides explainable rankings. Table 2 makes the benchmark feel real because it spells out exactly which tasks and datasets Iceberg uses and how success gets measured. This table shows the full dataset overview, including scale, vector dimension, embedding model, and a task label that defines relevance. The ImageNet block lists multiple embedding backbones, while the Glint 360K rows focus on identity labels for face recognition. The last 2 rows cover text retrieval with hit at K and recommendation with matching score at K. Figure 4 explains why high synthetic recall can still fail to help the real task, because information can leak out at multiple stages. This figure shows the full information loss funnel graphic, which frames end-to-end vector similarity search as a 3-step narrowing. The top layer is embedding loss, meaning the vector representation drops task-relevant details. The middle layer is metric misuse, where the chosen distance does not match relevance. The bottom layer is distribution sensitivity, where index behavior changes under data skew. Table 7 turns the synthetic versus task gap into an actionable leaderboard, because it names different winners depending on what you optimize. The left half ranks methods by query speed at the same synthetic recall, split into Euclidean distance search and inner product search. The right half ranks by query speed at the same task metric, so it reflects downstream utility. Commerce is a nice example, where MAG wins synthetically, but IP-NSW+ wins on the task score, so the preferred method flips. So, 2 takeaways stand out. Synthetic recall and latency scores can look excellent, while real downstream utility collapses, and the information loss funnel explains why by separating embedding loss, metric misuse, and distribution sensitivity. The broader implication is that vector similarity search should be chosen and tuned as part of an end-to-end task pipeline, not as an isolated index. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.